So what we're hoping to get out of this lecture is get some understanding of the NAS mechanism and the elimination addition mechanism when dealing with aromatic rings. And I would really kind of classify it at the end of our discussion of aromatic rings, because it's really having the aromatic ring act very, very oddly. So we've got two primary examples shown here. One is the result of an NAS mechanism, and the other one is a result of the elimination addition mechanism with regards to your aromatic rings. Okay, both of these are kind of odd. Okay, and so we'll address each of those issues. So first off, the type of reaction that occurs in both cases, we're looking at a substitution. Let's just leave it at substitute. Okay, so we're doing an exchange for the halogen, or the halogen for an OH, or in the second case, again, a halogen for an NH2. So on the surface, that isn't a big deal. We've kind of seen those reactions before, but the primary reason that this is kind of a weird reaction is that what we're exchanging, or what we're losing, is a leaving group. And when we looked at our EAS reactions, we haven't seen a leaving group. It's H plus being removed. That's definitely not a leaving group. And we could try and draw parallels back to what we've seen with the substitution chapters way back in first semester from your Smith textbook. I think it's chapter 7. So it's kind of odd, because even with those substitution chapters, we said halogenated aromatic rings do not react. Okay? So if we ran under the standard conditions as a review from our first semester, if we started with this bromine and then said, I want to do a substitution reaction with, say, cyanide. Okay? When we go through and do that, we end up with no reaction. It says it doesn't happen. So no SN2. Well, if we try to go through with just water, H2O, we still get no reaction. So those were our standard substitution reactions, or our standard SN reactions. And they didn't work. But now, after all that time between first semester and second semester, we're now looking at a reaction where we're absolutely showing that we get this reaction. It seems a bit odd. So we need to kind of look at it a little bit closer. So number one, we aren't starting with just a standard halogen bromobenzene structure. In the case of our NAS, notice that we also have this NO2 attached to the ring. That NO2 is electron withdrawing, extremely electron withdrawing. And it turns out for the NAS mechanism, that's really critical for this. Okay? We really need that electron withdrawing group. When we move to the elimination addition is even more weird, because we actually have an electron donating group. Okay? So even that doesn't seem to be consistent with either of these mechanisms. So maybe there's something else going on. So the next part would be to look at the reagents that we're adding. You'll notice in both cases that we are adding a sodium salt, okay? Either sodium hydroxide or sodium amide. Both of those species actually have something in commonality. They are both strong bases. Okay? Because they are also both small, they're also both very strong nucleophiles. So one of the first questions that we might come out with would be, well, which one's the stronger nucleophile, or the stronger base? You should be able to prove to yourself that the answer, go ahead and pause in 3, 2, 1, the nitrogen is our stronger nucleophile or base, because it has less electronegativity than the oxygen, meaning it's more willing to share its electrons, either to a hydrogen or to an electrophilic atom. So both of these mechanisms involve this strong base, strong nucleophile. You'll notice that the conditions for the elimination addition are relatively mild. Okay, and that might be a little bit more difficult for you guys to pick up on, but if you look up the properties of ammonia, Ammonia is actually a gas, so to get it in the liquid form, we've got pretty reduced temperatures. So as far as our temperatures go, we're looking pretty cold. In the case of the NAS, we're actually jumping up into a higher temperature range, 70 degrees. Not ridiculously hot, but pretty high up there. And the reason for that is that the reaction's not a very likely reaction to occur at all in either case. So we need to add a little bit of heat to clear it. When we move to the elimination addition, we don't need as much heat because we've replaced the energy with a stronger nucleophile or base. We're using that sodium amide. And so we've got all sorts of things kind of bouncing back and forth between these and trying to see what's similar and what's different. Okay? So what we'll go ahead and do first is think about that NAS mechanism. And this next slide is a bit busy with data on it, or words, and it misses all of the reaction stuff. Okay? So if you would for a moment, go ahead and pause and write down that structure within our black box. So you've got something to look at and kind of think about as we go through and look at the conditions for our NAS. So again, I'll give you a chance here to pause in 3, 2, 1. Or not. In a second here, we'll pop back. So we've got the summary of what's happened on each side, kind of the big things that's going on with each of those. So now we'll advance. We've got the starting material in the upper left-hand corner, and remember what that's going to turn into at the end of the NAS mechanism. If you can remember, you can draw it out on the upper right-hand corner. We've got the OH, okay, or our phenol. So it's a bit of an odd reaction because our aromatic rings are electron-rich. Okay, electron-rich, why? We've got a ridiculous amount of pi bonds within that structure. And those pi electrons are oscillating all the way around that circle. So our rings are classically highly electron-rich, which means they're going to act as nucleophiles. So they react with an electrophile, hence our EAS mechanism. The NAS mechanism switches things around. So now what ends up happening is the ring will act as an electrophile, which is very, very odd. It has a ton of electron density. It doesn't make sense for it to be attacked by something. Okay, so we need special circumstances to actually be at play to allow this to occur. So one of those first things, the ring must be electron poor. Well, if it's going to act as an electrophile, it needs to not have electrons, hence electron poor. This can be done by making sure our ring has deactivating groups attached to it. The classic one that we'll see would be nitros. Right, so you could see as an electron poor group, NO2 attached. You might see carbonyls. Okay, those are going to introduce another situation that we won't stress too much about, but we're looking at relatively deactivated rings. So we need that strong electron withdrawing group. Next big part of this is that we need a leaving group. The hydrogen that's getting substituted in the EAS reaction comes off as H+. If we're going to dump a nucleophile into the ring, I have to spit out electrons. So I can't spit out H- because it's a horrible leaving group. So to run the NAS mechanism, we need a good leaving group. The only real good leaving groups that we are aware of are our halogens. Okay, and we pick our halogens because they have relatively high electronegativity, which means they can pull the electrons away already. Okay, so high electronegativity, and then also minimal secondary chemistry. And I don't know how to spell. Let's try that again. Minimal secondary chemistry. What do I mean? Well, a lot of students will go through and say, okay, well, if I need something to take electrons away, we'll throw in oxygen, because oxygen has a very, very high electronegativity, so it tends to be a good option. Except oxygen needs 2 bonds, so you would need to add something else to it. And typically we'd add a hydrogen. Well, that hydrogen is now acidic. So if we pick our groups carefully, we can avoid that secondary chemistry if we throw in our halogens as our good leaving group. So halogens are classically the best leaving group that you're going to work with. Okay. Next part, and this one gets a little bit tricky, the relationship between the leaving group and the withdrawing group must be in this ortho or para alignment. And that seems kind of odd. To really get the answer to that, we're going to have to look at the overall mechanism behind it. And I will warn you that I did not actually do a digital drawing with no digital mechanism to look at. You're going to have to kind of take careful notes and look at what I'm drawing out. I'll try and be as neat as I can as well. So, let's take a look at two examples. We're looking at identical reaction conditions, sodium hydroxide, 70 degrees Celsius. We'll talk about the H3O plus in a second. And in one case, we do the substitution. The OH replaces the bromine. In the other case, we don't get a result. Okay, so as I said, we really need to evaluate the mechanism behind each of these. So let's go ahead and start with the one that works. Okay, so we'll pick this guy. And one of the points that we really kind of drove for here was that our nucleophile, okay, our OH minus, okay, we've got our OH minus as our nucleophile, and our ring must act as the electrophile. Okay, well, where should that OH then attack? Well, the simplest option, at least according to what needs to happen, is it's going to have to attack the carbon where the bromine is. Okay, that could be a bit dicey of attack. Very, very crowded. If it was an SN2 circumstance, we say, hell no, that's not going to happen. Okay, but we're going to have to work with this for a moment. So according to our basic substitutions, we say this doesn't work. This isn't a basic substitution, so let's just run through it and see what happens. If we do that first assumption, let's just say that happens, just that single arrow. We want to draw exactly what that single arrow shows. Well, I haven't touched anything else, at least yet. And if you are drawing this now, realize that you will have to erase it in a second. And we've got our bromine. Then we have our new bond to our OH. The result is that our carbon now has too many bonds. Okay, we've got a 5-bonded carbon. So it's not something you should necessarily panic about. Just realize that we now have to go visually back up to our mechanism and we have to add another arrow. Okay? When we're looking at doing our mechanism, what we'll do after this first attack is break the next most available bond. And we've got two options to look at. Two options. So I'm going to go ahead and erase the product, which I'm going to end up having to draw here again in a second. So if we look real closely, we're either going to break the carbon-bromine bond, or we'll try and break the pi bond. Okay, now the question becomes, well, which one should we break? If we break the carbon-bromine bond, we are 100% doing an SN2 reaction. That is an immediate push out of our leaving group by our nucleophile. And as we saw when we ran that experiment way back in first semester, that reaction does not work. Okay, so it doesn't make sense to have the bromine immediately eliminated. Okay, so we know that isn't the case for our mechanism, which means our next option is to look at the pi bond. Okay, before we even draw that out, let's pause and think about that. Does it make sense to break the pi bond before the carbon-bromine bond? What type of bond is the carbon-bromine bond? It's a sigma bond. So we're trying to break a sigma versus a pi. Okay, so we're going to be careful which one has higher energy. The pi bond is made with p orbitals. The sigma bond is made with hybridized sp orbitals, or spx orbitals, if you will. We don't know exactly how many p orbitals are involved. Which orbital is higher in energy? Think back to your atomic structure. If we looked at hybridization theory, there's our s orbital, there's our 3p orbitals. If we're now going to go through and hybridize to make, say, an sp2 hybrid, we're going to take the s orbital and 3p orbitals, and we would expect an energy for that sp2 hybridized orbital to be somewhere in between the s and the p, an average of those energies. And then we would also expect an unhybridized p orbital left over. What does that mean? That means that any orbital that has s hybridization should be lower in energy than our p orbitals. Extrapolate that now back to our reaction in deciding which bond should we break, the purple or the orange. The orange breaks a pi bond or using p orbitals. The purple breaks a sigma bond or the hybridized s orbitals. The pi bond makes more sense to go through and break than breaking the leaving group off immediately. Alright, so let's draw that out now and see what the result is to see if that's even a valid move. So again, we'll draw out our benzene structure. We've got our NO2. There's our double bond. We've got our bromine. We've got our bond to our OH. Okay, and now we also have a lone pair sitting on this carbon. Okay, and hopefully you all at this point go, oh my god, that's a horrible structure. Okay, or that's a horrible thing to do. And it's a horrible thing to do because we've lost aromaticity. Just like the EAS reaction. Okay, and just like the EAS reaction, what do we end up doing? Well, we see if we've got resonance, something to stabilize that negative charge. Except in the EAS, we were looking at stabilizing a positive charge. In the NAS, we're going to look at stabilizing a negative. So we'll take the electrons down, form a new pi bond, which would mean our carbon would have too many. We'll take the next pi bond and drop it immediately on the carbon atom. The result of our arrow pushing, and here, there's our bromine, there's our OH, come on, give me a second here, there's the OH. We now have a new pi bond and we have a lone pair sitting on that oxygen. We could again do resonance, push that around, and we end up with a new structure, or a new resonance structure. And since I've been color coding, let's very carefully erase that guy. Color code that in. Our lone pair there. Before you yell at me, yes, I'm about to drop in the nitro. Okay, just like with the EAS reaction, we have to draw out all these resonance structures to represent that we do have a stable system, or we've got something stabilized. Within this, we actually have the answer to why our nitro needs to be in the ortho or para positions to our leaving group. And that answer lies, because it's dirty, evil person, right, lying, right in the middle in that blue structure. So again, take a second to pause. We'll talk about the answer in 3, 2, 1. To help you see that answer, let's draw the Lewis structure for the nitro. What charge is that nitrogen? It's positive. It doesn't want to be positive, so what can happen? I've got the option of taking the electrons and sliding them into a pi bond between the nitrogen and pushing electrons out onto the oxygen. This additional resonance structure is what stabilizes our intermediate and allows it to have enough time to exist. So this is our clutch resonance structure. If you think back when we talked about the EAS reaction, we ended up finding a clutch resonance structure that either made the para-ortho substitution a favored situation with a a better resonance structure, or it was in the case of our meta substitution where one of them, our para-ortho systems, were horrible. Okay, so go back and take a look at those EAS resonance structures to see what's going on. And in this case, this structure stabilizes the intermediate, and we would expect this horrible, ugly looking aromatic thing to be relatively okay. The very final step of this is now saying, you know what, I don't want to be this crazy negative intermediate anymore, and we can take the lone pair, donate it back into the pi system, but now our carbon has too many bonds, so now we kick out the leaving group. Okay? And in this case, the bromide is a much better leaving group than the hydroxide. So we may have lost aromaticity in the course of the reaction, but the net result is that I'm now comparing Br minus as a product versus OH minus as a starting material. Bromide is a much more favorable system to have. In my equilibrium, I would expect to push towards the products. Okay? And in all of this, the clutch of that was that that electron withdrawing group could stabilize the intermediate long enough to allow that equilibrium to establish and to give us the substitution product. If that first step is so disfavored because it generates such a small amount of product, then we can't ever move forward for our very last step to make our product. Okay? So it's all about that resonance stabilization. And in this case, we're going against the grain or the nature of the aromatic ring. We're asking the aromatic ring to act as an electrophile. So this already is a disfavored process, so that intermediate better be wicked stable to allow this reaction to occur forwards. Okay? So then, of course, we would then ask the next question. Presumably you have more questions, but you can ask me later. Why, when we go through and do the substitution pattern where our nitro and our bromine are meta to each other, do we get no substitution? Well, just like we did for the case where we got substitution, we should go through and test it. So we take our hydroxide with its negative charge, we do the attack, we do the resonance, and we generate our first, or we do the attack, we generate our first structure. Draw this guy out. There's our NO2. We've got our lone pair. We've got our OH. And if we go through and try and draw our resonance structures now, whoops, let's not do that in black. Our electrons move down, charge moves across. What ends up happening? You'll notice that we do not put negative charge on the carbon that has the nitro. Okay? You can continue to draw resonance, and what you'll end up seeing is that we end up putting the negative charge at all of the positions except the carbon, well, not all of them, but at several of the positions around the ring, but none of the charge will ever make it to the carbon with the nitro. Without that extra stabilization of electrons, we don't see this reaction occurring. That means that this first step's equilibrium, okay, in this case, is now so disfavored that as soon as that OH attempts to attack, it immediately takes its electrons back. And we go right back to our starting material. The OH can't get in there and our intermediate be stable for long enough to actually force the bromide off. And instead, what happens? The bromide stays on, the OH never attacks. Okay? So by looking at those resonance structures, we can start to come up with explanations for why one works and one does not. So remember, beginning NAS reactions, very disfavored. They are not good reactions to run because aromatic rings are not electrophiles. They're horrible electrophiles, okay, because of all of that electron density. if we give them a strong enough nucleophile and we withdraw enough electron density away from the ring, we can trick the aromatic ring into acting as an electrophile. But all of our conditions must be perfectly right to allow for that to occur. Okay? So one thing that I like to kind of mention with this is that we might ask, well, how would anybody figure this out? Well, more than likely, at least my theory, is that someone went through and made a very large structure, okay, that probably had some chain coming off of the end of that, whatever that chain may be. And perhaps at the end of that, they had some carboxylate, maybe even a carboxylic acid. And they just wanted to deprotonate it. So they added the OH in the hopes that it removed that hydrogen. Probably did. But then they also ended up with this other weird product. And I'm like, well, what the heck happened here? Where did this bromine go? Why do I have an OH in my IR now when I should have nothing? It's probably an accidental discovery. At least that's my initial guess at its possibility. Once we found this anomalous result, we then back through to try and figure out how it happened. Okay, so this is what we've got to work with. It's here. Deal with it. One thing that's kind of special about it is that if you look at a product and it has an OH, so you have a phenol functional group. So the phenol, if you remember correctly, is the alcohol directly attached to a benzene ring. The only way that we can get that right now is through the NAS reaction. So if you see an OH on your ring, now you need to know that you need to do an NAS reaction. So that's your one big trigger for it. The other thing that we would then look at, okay, is what happens if we go through and change the reaction. So, hey, someone maybe accidentally got this to work with the nitro, but they're now like, oh, that's really cool. I want to go through and do it with something else. So they go through and try the sodium hydroxide with just a standard chlorobenzene. They heat it up, they run it, they get no result. They go, well, that kind of sucks. I wanted to do that substitution reaction, but I didn't want to bring in that nitro. So then somebody else goes along and says, well, you know, if it doesn't work with a little bit of heat, let's add a lot of heat. So that's what they did. They cranked the temperature up. 350 degrees Celsius is not a nice temperature. A lot of organic materials will decompose at that, so it's not a very nice reaction to run as far as organic chemistry goes. But if we jack up the conditions, sure enough, we can see the NAS reaction working. We do see that substitution. Okay, well, somebody else came along with a little more refined touch and said, well, there's other ways that we can speed the reaction other than adding just brute force heat. We can increase the reactivity of our nucleophile or electrophile. And in this case, they decided to take a look at our nucleophile. So they switched it up and said, what happens if I jump it up to the NH2? And sure enough, when we moved the NH2 as our nucleophile, we can use relatively, we can use relatively mild reagents. Like I said already, liquid ammonia, not easy to make. This has to be relatively cold, so we're running at low temperatures to get this. So instead of adding brute force heat, we change the strength of our nucleophile, boom, we can get the reaction to work. Okay, so two pseudo triggers for your NAS mechanism. If you see an OH, it's NAS, period. If you see an NH2 on your ring, it was potentially added through an NAS mechanism. But remember, there's another way you can get the nitro or the NH2 on your ring. Hopefully you remember that. If you get the nitro on, you can then reduce it. The one I happen to remember, I believe, is the tin and hydrochloric acid, and that will actually take your nitro down to an NH2. So we still can get an NH2 on there without doing an NAS mechanism. Okay, so that one's a little bit trickier to worry about. You've got to be a little bit more careful. So if you see OH, NAS. If you see NH2, it's kind of a coin toss. You got to take a look at and see what you've got. Absolutely, for the NAS, you need the halogen leaving group. So if you see the halogen, NAS. Okay? So, someone started to play around with this some more just to see what was going on. Just, you know, a little S&G. When they added another substituent to that chlorobenzene structure, and they looked at the products, they noticed kind of an odd result. Our NAS mechanism really only predicts the formation of that one, our direct substitution. So why on earth do we get this other substitution? That just seems so weird. Okay? And that's kind of the birth of our elimination addition. So again, these probably happened through lab discoveries. We aren't doing this and someone didn't sit down and say, oh, I'm going to add this, oh, this is how it works. No, they probably took a guess, thought it was going to work, and got something way whacked out weird, tried to figure out why. Okay? So it's that piece that's the weird, odd why, and that's the one we're going to try and talk about here. Kind of a neat one. How much information? Okay, so let's take a look at our NH2. The NH2, as we already discussed, come on, pencil, if we get rid of that sodium, okay, which should pretty much free float away from it, we've got a really strong nucleophile. But because it's small, meaning it can get into tight spaces and other spaces as well, it's also a pretty good base. So our NH2 can act as both, and that's where we run into some kind of issues with this. And what do I mean by that? Well, if we go through and see where the NH2 substituted, you'll notice that it substituted really around just 2 carbons. Okay? And we can circle those. We've seen reactions before where a nucleophile goes to slightly different positions around a pi bond, but in the process we lost the pi bond. So that seems kind of weird because we didn't lose the pi bond here. Or did we? Okay. So they repeated this experiment, get rid of that methyl, let's kind of stop that. And they repeated it with this radio-labeled carbon. So we changed the carbon to carbon 14. And we go through and run the reaction again. We get pretty much the same result as we expected with our chlorotoluene in the previous case. Except now we don't have the methyl messing with this. And we notice that we get pretty much a 50-50 mixture of products. Again, very, very odd. Our amine is only being added across the 2 carbons next to each other. No other position away from that radio-labeled carbon. Seems very, very weird. Okay? Is there a functional group that activates 2 carbons for potential chemistry? So when we talk about functional groups, and I told you need to have them all memorized, this is one of those cases where we need to have them memorized. What functional group? So if I draw out 2 carbons, gets me chemistry, so some sort of reactivity at both those positions. Hopefully one you might pick up would be the aromatic ring. That's too many carbons, so let's simplify it. There's the alkene. And alkene works. We do get that chemistry there. But we start with what we could call an alkene in both cases, and the alkene didn't really change. It stayed an alkene. Well, isn't there another functional group? Say with another pi bond? And now you're going, yeah, that's true, but that's an alkyne. You can't put a triple bond in an aromatic ring. I challenge that theory. Turns out you can. All sorts of weird craziness goes on with this, and this is probably one of the reasons why we talk about it, is just because it's bizarre that this happens. The NH2 acts as a base. So in that very first reaction that we've got shown up there, we have an acid-base reaction. The NH2 acts as a base and pulls off the hydrogen, which now puts a negative charge on the ring. Well, a negative charge freaks out and needs something to stabilize. So what it does is it shifts that electron density towards the most positive atom, which is the carbon with the halogen leaving group. The leaving group then leaves, and now we have this wicked crazy intermediate, the benzyne. Okay? What is the hybridization of the benzyne carbons, or either one of them? Kind of a tricky concept. We look at the groups of electrons, it's one group, two groups. We're looking at an sp carbon. Highly unstable, very, very odd that it even happens. But if you pull out a model kit and look at the molecular dynamics of it, we can actually drop a triple bond into the structure, and we end up with this weird folded thing. So it's kind of a neat thing if you want to do a Google search for benzynes and look at that folded structure. It's kind of bizarre. Some people may ask, well, why even think to go into the benzyne? Well, why think about it? It has to do with the product. Our product showed up at 2 positions on our carbon. We don't have a choice. Okay? This is our thought process. We have to get reactivity at both of those carbons, but the chlorine, is our leaving group, is only at one of the carbons. So we have to put in this reactivity. So someone went through, said, okay, we're looking at this very odd kind of pseudo-radical triple bond kind of situation, and then use that to predict both the products. Because the benzyne is now the benzyne and that triple bond and all the electron density is all sorts of convoluted and folded up on itself, it's actually primed to break open. And that break open happens by now our NH2 as a nucleophile. Okay, so yet again, another weird case. Why on earth would a triple bond act as an electrophile? It has tons of electron density. It does, but that electron density is, for lack of a better description, confused. It has no idea what's up or down, so it's just ready to move. The NH2 can come in and attack that triple bond from either or at either carbon. The result is that we end up doing an addition of NH2 and hydrogen in the subsequent step, in the subsequent acid-base step, across the triple bond. So we do an addition. Both those steps gives us our addition, and to get to the benzyne intermediate, what did we have to do? We had to do an elimination. So when we talk about different mechanisms and how they're how I've mentioned that they're combinations of these 5 mechanisms or reactions that I've told you to look at, it's for a good reason. The case of this NAS version type reaction is an elimination followed by an addition. It's a more complex mechanism or a more complex reaction that's based on the 5 quote-unquote simple ones. Okay? So after all of this, we've got a couple hits that we could run into. Number 1, you don't believe me. Okay? I didn't believe it either. There's no way that we could make this benzyne. Okay? There's got to be better evidence or a better explanation somewhere out there. Well, guaranteed a scientist didn't believe it either and said, if you're going to make this crazy benzyne structure, really what I've got is now a super reactive pi bond that is willing to react with anything available. So if this structure exists, I should be able to react it as a pi bond. Okay, well, did we start off this whole section of the material, beginning of the semester, with looking at reactive pi bonds? Yeah, we did. We looked at the reactive pi bond in the case of a Diels-Alder reaction. So if I have this pi bond, I expect that I could react it with a diene. if this benzyne structure really did exist, I had better see the Diels-Alder addition. If it doesn't exist, it can't be there. Okay? Sure enough, they pop it in, run the Diels-Alder reaction. What do we get? Oh my gosh. Who would have believed it? We get the cycloaddition product where we actually still have the benzene structure intact at the end. What does that mean? That means we had to have had a triple bond in our starting material, otherwise the reaction wouldn't have worked. As crazy as it may be, the benzyne is here to stay. You're responsible for knowing what's going on within that mechanism. Okay, so you're looking at lots of negative charge, so we go back one or back two and look at kind of the stepwise breakdown of your mechanism. The nitrogen from your base removes the hydrogen in an acid-base reaction. That then does an elimination step to kick out our leaving group. We now have formed our benzyne. Once we have the benzyne, we can now do a nucleophilic addition, okay, also kind of a bit odd, to form our anion on our ring, which can then pick up a hydrogen in an acid-base reaction. So when we're looking at the elimination addition mechanism, it's a lot of negative charge. Okay? When we looked at the EAS reaction, we looked at a lot of positive charge. In the elimination addition, we are dumping electrons into the ring. Our ring has to become negatively charged. Bit obnoxious, bit tricky. It's the way it is. Last little question we throw in here. Why not look at, say, perhaps standard addition reactions, HBr or Br2? Well, what were the reagents that we needed to start with? For this reaction, we needed NH2, which was a strong base. What is the base going to do with our HBr? Acid-base reaction, neutralizing our reagent. Can't run the reaction. Why not use something like bromine? Good option, might be a possibility. Maybe somebody has done it. I don't know. It's just less impressive than using the Diels-Alder. So we use the Diels-Alder. Okay. So here we are at the very end of all of our lectures for our first exam. Here's all of our aromatic reactions, again summarized with all the kind of important detail that I think you would kind of need to piece together. You notice that we've got the NAS and the elimination addition now at the very bottom, trying to show you kind of what's going on with those. Remember, both the NAS and the elimination addition are using strong nucleophiles, hydroxide or amide, so OH minus or NH2 minus. Those are necessary to get this reaction to work, the NAS and the elimination addition. You're responsible for being able to string all of these things together. I wish you the best of luck with it, and I will talk to you when we meet again. If you've got any questions, feel free to send me an email.